All right. Good afternoon. My name is Eric Ferreira, and I have Phil here with me. He's introduced himself from King. That's the time where I tell you to stop looking at your phones unless you're playing Candy Crush. If you're playing Candy Crush, you're fine, okay? But otherwise, please stop. Today, we're going to talk about best practice of Redshift. And it is pretty much, I keep having the same presentation every year. So this year, I decided to make something different. Instead of saying, here's what documentation says you should do, you should not do, we're going to go over a particular example of one customer that went through themselves and learned the process. And then I will show you some things under the hood of Redshift, how it was designed, so you understand why the best practices work and why the anti-patterns don't work. So then you can have like a first-hand experience of, oh, that's why you should do this or should not do that. And so that's the plan for today, right? So we're going to go over a brief recap of Redshift. We're going to go over a King implementation of their CRM within Redshift. And then I'll come back and walk you through the whys of his best practices work on Redshift. OK? Sounds like a plan? Now, what is Redshift? Well, Amazon Redshift is a relational data warehouse, massive parallel petabyte scale, fully managed database, and you have different platforms to choose for. And it's pretty much $1,000 per terabyte per year, or you can start playing with 25 cents per hour. So that's Redshift. Now, that's Redshift for you. For us, here's what Redshift is. Redshift is a Postgres database where we got the storage layer wiped out, and in its place, we created a columnar storage where on a regular database, all the columns are together on the same row, on the same record, like a file. On Redshift, every column has a separate file for itself, so you only touch the columns you need. It's a massive parallel cluster, a share nothing cluster, brute force, multiple parallel processing. And we put a OLAP SQL engine on it that it can take those big, ugly queries you guys write all the time, and it can take care of those and make the query run fast for you. Now, we wanted to make that to run as a cloud service, right? So it's on AWS. And to run on AWS, there's a lot of automation that has to happen on different places. And because AWS is sort of a Lego store, we pick up those pieces from other services on AWS to help us with that. We didn't design a lot of things from scratch. So we are big users of AWS ourselves. So we started using the simple workflow product from AWS. We started using Amazon VPC so you can protect the data around the network around your databases. We have IAM so you can have access for users for the console access. We use Amazon EC2. Our hosts are EC2 hosts, the same ones that you can use on your systems, right? We use Amazon S3 mostly for our backups and our intake of data. We use KMS for key management. We use Route 53 for our network management for your end of point for access to the database, right? And we use CloudWatch for monitoring and alarming. Right? All those are standard products that are used in the same way that you would use. You don't have any special API, any special access. We use the same way as you. And that together makes the service Amazon Redshift. Now, inside that availability zone on Redshift, Redshift is always inside a single availability zone and inside of a VPC, a virtual private cloud. And it lives on a particular region. And there are things you can do to restore a new cluster on a different AZ on the same region, or you can push your backups to a different region. But in general, like on a basic level, Redshift lives on a single AZ. Now, we launched on February 2013. It was a Valentine's Day. It was a lovely Valentine's Day when we launched Redshift. And since then, we added 135 features, significant features to the system, and we never raised the price one single time. Now, who here uses Redshift today? Show of hands. Awesome. Great. Great to have people. Now, I'm going to pass the baton to another user of Redshift, and he's going to share with you how they did the implementation, how they learned the best practices on real life.
Brilliant. Thank you. Thanks a lot, Eric. So, first of all, who of you have heard of King before? Not that many people, but who's heard of Candy Crush before? OK, a lot more people. So King is basically the company behind Candy Crush. When I was asked by Eric and his colleagues if I would like to talk alongside him and explain our journey of Redshift, I was very honored and was very happy to be able to share our journey. We've been using Redshift at King for 2 years now, but my experience of Redshift actually goes back quite a bit further. Before King, I was running a company called Comify. We were a big not big, but we were a marketing technology company. And at the beginning of 2013, we started acquiring a lot of customers. We had a lot of big clients in the gaming space, but also in media and quite a few other things. So we really needed to ramp up our systems. At the time, we were running a Postgres cluster, which we're really pushing way beyond its limits. What we then needed was to really upgrade our database technology. We went out, we researched a lot of different solutions, but none of them really scaled to the point where we needed it. And then, luckily, Redshift came along, and we were actually blown out of the water by the performance. And as Eric just said, Redshift was launched in February 2013. May 2013, we're already running in full production and managed to scale to the point where we needed to. So I'm personally as well very grateful for the performance. What I like to do today is go a bit more into detail what we're actually doing at King. So Amazon Redshift as an operational CRM database at King is the title. The key here is the operational piece, because I believe we're actually using Redshift quite differently from a standard data warehouse operation. We're actually using it to power our marketing system, which is constantly sending messages, engaging our clients. But let's go into the business challenges first. What do we have? We have a very dynamic customer base. We have a very large scale with 100 millions of users, players at King. But we also have limited data science resources, pretty much like any other company, I believe. So we've just seen, quite a few of you guys know Candy Crush Saga, but let's look at what actually happened in the CRM saga before Redshift was being used as part of a marketing system. The saga looked a little bit like this. So a marketeer wanted to do a campaign. They thought about, okay, who do I want to target? What do I want to send out? They then put that into an email. It went over to a data scientist, who then did the extraction together with an engineer. Once they've done that, they put that back into an email. It went back to the marketeer. Campaign was executed, and the cycle continued. The Candy Crush bubblegum troll really didn't like this because it took up to a week sometimes for this process to finish. So it wasn't really feasible for us to continue that. Especially if you look at the scale we're operating at today. So let me give a little bit of a background of where we're at the moment. So we're sending about 9,500 campaigns on a weekly basis. We are sending about 1.5 billion messages on a monthly basis. We're supporting 12 games, and we're doing all of that with only 8 promotion specialists who are the marketeers that are actually running the campaigns and executing that. So I think these numbers are very impressive. But I think they're even more impressive if we put them into perspective where we've actually come from within 2 years. So before Redshift, we were running about 5 campaigns per week. We were sending only 23,000 messages per month. We supported only 5 games, and we did all of that with even more people. We had about 10 people dedicated to running that. So I think a very impressive increase in terms of scale. I talked quite a bit about the marketeers and that they need to run the system by themselves. So let me show you what they're actually using to engage with the marketing platform. They're using a campaign manager, which is called Emisario. In Spanish, Emisario is the messenger of the king, which I think is quite fitting for us. So what you see here is, on the left-hand side, you've got a query builder. So the marketeers can use very simple and/or logic to construct their campaigns. So they might say, we want to message people that live in Las Vegas, they've played within the last 14 days, and they're above level 100 in a particular game. So they can do that. And then the blue bar on the top right-hand side gives them pretty much immediate feedback, because we can query Redshift very quickly, and the marketeers get quick feedback saying, this segment has X number of players, so they get a really good feeling how big their campaign is, and so on. So once they've done that, they can quickly click apply and execute a marketing campaign back on the back of the data we've actually just retrieved from Redshift. But what do we actually like about Redshift? So for us, it's been very quick time to market. It's been very scalable, great value for money. We're holding billions of customer records in our system. We're doing more than 10,000 queries per day. It's great that we don't need a dedicated admin team to run the cluster. We're getting great support from our friends at Amazon. The columnar-based and massively parallel nature actually fits our workloads very well. And the execution times of the analytical and marketing queries are actually very, very quick. So to sum up, we love the performance we're actually getting from the system. You might wonder, how big is our cluster? So we're running 3 clusters here. So the bit on the left-hand side is not drawn to scale at all, otherwise you wouldn't be seeing it. But in development, we're running 2 DC1 large nodes. In staging, it's 6 DC1 large nodes. But then the big daddy in production, here we're running 24 DC1 8X large nodes. And they're all EC, so compute nodes, because for us, the computation is more important than actually the storage. I think at the moment, we're only running off 30, 40 terabytes, so not that much storage, but we need a lot of compute power to return the queries in the time we need. So how does Redshift actually fit in the overall architecture we have? So key for us are obviously our players. So they play our great games on their devices. From the devices, the data goes into the game servers. From the game servers into the legacy data store. From there, we're doing regular ETLs that are going into S3. Redshift then takes the data from S3. And the emissarial server here is the back end to the front end you saw a minute ago. And that then queries Redshift and gets the user data out of it for the marketing execution. And once all of that's done, the emissarial server sends the data to our delivery servers, which communicate with Facebook, Google, Apple, and so on, which then deliver the messages up to the devices. And then this lovely circle continues. Great, so let me quickly sum up the requirements we're actually having for Redshift. So we need a database that be part of an operational system. That means it must handle a lot of parallel queries. So we can't have a big query blocking everything, because there are a lot of background tasks for continuous operation of campaigns, but also marketeers are engaging with the system constantly. And for the marketeer queries, we've given ourselves a maximum of 15 seconds it can take for a query to return, because we want the marketeers to have a great experience with the system, not needing to wait for things to come back, because if it takes like minutes, they'll get bored, they do something else, they forget about it, and our players are not really getting the great experience they deserve. So 15 seconds is the threshold we set ourselves. And obviously, it must be financially viable. So we can't have an unlimited number of big instances. Let me do a big cut here, because here what I've done so far is giving you a bit of the background, what our scale is, what we've done, and what the requirements are for the system. What I'd like to do now is to actually dive into real examples and share the best practices we've learned over the years we've actually used Redshift at Anger. So first one, and very important one, is the proper use of distribution keys in all joins. So we're having tables that have more than 4 billion rows. And as you guys probably know, at such a scale, only merge joins are actually a viable solution to get anything out of the database. So we did that. We queried the database, but still, queries were running pretty much forever and never returned. What we found was that we actually need to put the distribution key inside the query. Semantically, it's redundant, but by adding it, Redshift doesn't need to scan across all nodes to actually get the data out. So it can stay in a single node and will be very quick returning the information. So Eric later on will actually explain a lot more technical details about the best practices I'm sharing. So distribution keys, key in all joins, very important. That also leads me on to what we've done actually with natural distribution keys. So at King, we're updating about 10% of our data on a daily basis. So a lot of the data is constantly changing, which means we need to do a lot of updating and merging of data. And what we had at the beginning, we had a distribution key that was local to Redshift. So as soon as the new data came in, we needed to compute it, do the updating of the data, and so on. And what we found, this process took actually more than 24 hours to complete. So not viable at all. What we then did, we started searching for a natural distribution key within the business. So something the new data has, as well as the existing data within Redshift. And for us, there is quite an obvious one, which is the universal player ID that any player within the King network has. So we use that inside Redshift. And then when the new data comes in, we can use that again in all the joins, doing the merging and the updating. And we dramatically reduced the time. So as I said, it took more than 24 hours. And now we're running at about 30 minutes, and most queries are and most updates are actually happening in less than 5 minutes. So a great performance increase. While we're on the topic of updating data, as I said, one of the big requirements for us is to have Redshift running as part of an operational system, which means we can't have massive write locks all the time, saying, right, lock the tables, we're doing the updating, once we're done, we're releasing everything, and operation continues. We need to make sure that the system can continuously operate at the same level of performance. So what we've done is we're actually taking the data, we're copying it into temporary tables, and the temporary tables are inside Redshift. So it's not an operation happening outside Redshift, but it's happening inside Redshift. And we're doing all the merging, all the computation, everything we need to do to add the new data with the temporary tables. And from there, we're actually copying the temporary tables over. So we only have very short write locks, and we're getting a great performance out of the system. Next one. So next one is quite a funny one for us. Column compression encoding. We thought it would have maybe 5, maximum 10% of performance increase. And our friends at Amazon were very, very insistent with us and saying, no, guys, you really need to make that change. And they even sent 2 engineers down to Barcelona helping us to find the best encoding for us. And we had a very, very pleasant surprise because we achieved a very heavy reduction of I/O. We had a nearly 100% performance increase. And very nice was that we could reduce the cluster from 48 DC1 XL large nodes down to 24. So a massive reduction in cost as well, which obviously made the business very happy. But one notion of caution here, we did a lot of testing and experimenting to find the right encoding. So you can't just employ one, but you need to actually look and see which one fits the best to get the right performance levels of you. So this was, as I said, very, very good and nice surprise for us. Now on to concurrency optimization in WLM. So as I said, it's running as an operational system for us, which means a lot of parallel queries. Marketeers are doing queries. The system is executing a lot of campaigns in the background. And the marketeers found that often the queries return, as I said, within the 15-second threshold. But sometimes the queries took a long time, even though just beforehand they took only, let's say, 5 seconds to return. So they came to the engineers and said, look, the system is broken or something is happening because the queries are not returning properly. We started digging, but what we found was that the average completion time of a query was on average the same. It stayed within the threshold. So then we started digging more, and we found a great query within the GitHub utils Redshift is providing, which actually gives you the time a query stays in the queue before it's being executed. And bingo, here we found that quite a lot of the queries are actually queuing for quite a while before they can execute, because this number should ideally be 0 here to get the best performance. Luckily, there was a great easy fix for it. We basically increased the number of concurrent queries we can run from 5 up to 10. You might think, oh, the guys just doubled it because 10 looks quite a nice round number up from 5. But we did actually do quite a lot of experiments to find the right number for us. And I would urge you to actually do the same, because if you up this number too much, you can run into out of memory issues as well with Redshift. So again, quite a bit of experimentation is a good thing to do here. Now, as I said, we're getting a lot of new data into the system constantly. And that means we need to modify the data. At the beginning, we thought, great, what we'll do is, as soon as a new piece of data comes in, we update the database. So we were running concurrent modifications of the data. But actually, we ran into a lot of errors here, which resulted in quite a few rollbacks because we're accessing the same tables at the same time, which obviously the system doesn't like at all. So we opted for a very straightforward fix here, which is going from parallel to sequential processing and updating of the data. For our data freshness requirements, that is more than enough. But maybe you have more stricter data freshness requirements, so you might want to do it in parallel. But just a notion of caution here that you might end up having quite a few rollbacks as well. Now on to vacuum. I'm sure most of you don't like vacuums too much. They block the system. They're often quite challenging to manage and require quite a bit of work. Same was true for us. We opted for the standard 24-hour vacuum cycles. But because we update, as I said, about 10% of our data constantly, what we found towards the end of the 24-hour period, the performance of the database was degrading quite dramatically up to the point where it really wasn't responsive and we couldn't provide the right service to the marketeers. And the reason for that is, if you start updating data, Redshift doesn't do a straightforward update, but what it actually does, it does an insert and a delete. So you end up actually having quite a lot of data skew or data distribution skew within your tables, leading to big fragmentation of the data, which means performance goes down, and it just takes a lot longer for the queries to return. So what we then did, we went from a 24-hour vacuum cycle to an on-demand vacuum model. So we actually wrote our own system here that's making use of the SVV table info system Redshift provides. And we've set a threshold per table where if the performance goes below and falls below this threshold, we're actually doing an on-demand vacuum. And this had a great effect. So performance was stable. System is running at the same speed across the board. But also, it meant the vacuums didn't clog up the system or block the systems because they didn't have as much to do. So it was a great solution for us. And I urge you to actually look at the information the Redshift system is providing, so you can see if this is something you should potentially do as well. Now, this is a funny one. So reduce the number of selected columns. For you guys who have only used columnar data stores, this one is probably extremely obvious. We've come from Postgres, so OLTP background. And obviously with OLTP databases, you don't really get a performance penalty if you select more columns than you actually need, because you've already got the row with all the information you need. What we have in our system, as I showed you with the user interface, the marketeers are putting the query in, and then we have a system that actually translates what the marketeers have put in into SQL statements to then return the data. And this system was a legacy system which we initially wrote for Postgres. And the system often selected more columns than they were actually required. So we went back into the system and we did a lot of heavy optimization, making sure that we only select the columns that are actually required in the query, which again gave us a big performance gain. So as I said, not one for everyone, because for quite a few of you it's quite obvious, but if you have an OLTP background and you're moving over to Redshift, that's something to keep in mind. Another very important one for us, batch sizes, because we're constantly reading a lot of information for our segments from Redshift. We started with batch size of 100,000, but we found the performance wasn't great. We then started experimenting, and we increased batch size to 1 million initially. And what we actually found was that the batch size is not scaling linearly, but a lot better. So doing 100,000 or 1 million took about the same time. And what we opted for in the end is a batch size of about 5 million. Redshift can actually do more and still return very quickly, but that was actually due to our emissarial system. So what's actually connecting with Redshift is the limitation here. However, the limitation of 5 million, as I said, is due to the external system, but Redshift does have a limitation, especially if you go way beyond the 5 million. So we quite often do extracts of data that are ranging in the area of 100 million, 200 million at a time, or even more. And at that point, the leader node can actually become a massive bottleneck, because you're collecting all the data, you're funneling through the database driver, through the leader node, out to your external system. What we found, thanks to our friends from Redshift who actually pointed it out to us, we found quite a nifty feature of Redshift, which can actually unload data to S3 directly from a node, not having to go through the leader node. So if we have really big exports of data, we are writing directly through S3. However, here you again have to watch your distribution key very carefully, because if you don't, there's a big chance again it scans across all the different nodes and you have a massive performance issue. So if you have the distribution key in order and you have a lot of data, actually doing the unload command can give you really big performance gains. Great, so these are our best practices, what we've learned over the time. What we've done as well now is we've actually put them into definitely do, medium do, and do it if you have some time. Really important one, use distribution keys that can be used in all joins. Migrate to a natural key if possible. Reduce the use of the lead node as much as possible. Column compression encoding. Then on the medium side, data pre-processing outside the main tables, WM optimizations, reduce the batch size as much as possible, and if you've got some time, prohibit concurrent modifications of data, reduce selected columns, and do some on-demand vacuums based on the state of the table. If you guys have any other ones, I would really love to hear from you afterwards. So please come up and have a discussion afterwards, because we also want to learn from you and see what you've done, so we can hopefully increase the performance even more. And now over to Eric again, who will give you a bit more technical details.
All right, so thank you very much. Right on. So when you build Redshift, we build Redshift with three things in mind. We want it to be fast, cheap, and easy to use. It's like you have a Formula One car, but it's a self-driving Formula One car that it costs like a Toyota Corolla. Okay, that's the idea. Okay, or if you think about a toaster, we want it to be like a toaster. You submit your job, choose a few options, and it runs. Right? But we can't not know how the system works, otherwise you can't take advantage of its strength or appreciate the trade-offs you're making. For example, on a toaster, or even on those kind of simple toasters, we have a bagel button. Now, who knows here what a bagel button actually does? Very few people. Awesome. So if you want to know, stick into the end. I'll tell you what you're going to do at the end of the presentation, okay? But for you to appreciate Redshift, you have to understand how it was designed and how it's under the hood and how it works. So if you think about the architecture of Redshift, you have a leader node that is a node the same type as the node you choose for your compute nodes. And by the way, you don't pay for the leader node. So if you create a 10-node cluster, you actually have an 11-node cluster. And the leader node is on us. Right? It's the same type and module and memory as the compute nodes. And the compute nodes underneath is where the data resides, and data gets processed massively in parallel, and the data goes in and out in parallel through the compute nodes, either from S3 or EMR, DynamoDB, or any SSH server you can put your hands on. On the leader side, it's where you put your SQL endpoint, and all the metadata is stored there, and all the coordination of how the queries run happens on the leader node. Now, the idea for the Redshift to be fast is to reduce I/O. So we want to make as little I/O as possible. And one thing we did when we designed Redshift is to make it columnar storage. On a regular database, you have a row that has all the columns together. And if you query one column, you have to bring the block with all the other columns together. And data warehouse applications normally have very wide tables. So it becomes a very expensive proposition. On Redshift, if you only query a particular column, you only touch the blocks for that column. And that reduces a lot of the I/O. And that's why select star, it's a crime. It should be prohibited, right? It should be like banned, right? It's a bad practice anyway for application purposes because you never know which columns are going to come back. But on a columnar database, it's even worse. So that's why we try to reduce the I/O by only touching the columns you need for your query. Now, the other thing we do is to allow data compression of the columns. And because the system's columnar, you can have a different compression for different columns because every data type has a better compression, depending on which order it is, if it's an integer, or if it's a date, or if it's a varchar. So you can choose different compressions. Now, the system helps you by doing a sample of your data and compressing all possible ways, and then tell you which one came out smaller. But it's a sample. You might know your data better, and you might know the compression algorithms better, and there is trade-offs. Usually you spend more CPU to compress and uncompress the data. But data warehouse applications normally are they are I/O bound, not CPU bound, which translates to pretty much we haven't found a situation for large tables where compression doesn't make any faster. It always makes faster and makes it smaller and cheaper, like he talked about being able to reduce to by half the size of their cluster, right? And the other thing we do is something called zone maps. And that's a departure from the regular database. Regular databases, you might have to scan the whole table, right? You call linear scan, right? As full table scan, as other people know. And when you do that, a system like Redshift, you do that really fast because we multi-parallel, brute force, massive parallel data. It runs fast. But imagine you don't have to touch every block to know to get the right data you're looking for. On other databases, you have an index or projection or some other name where you have a redundant copy of the data in a different format, a B-tree or a hashed index or something that allows you to navigate to the data you want and then only get the block you want. On Redshift, every block of every column has a header that remains in memory all the time that has the min and max value of that column on that block. So when you're scanning for a particular value, we look at the header in memory first. If the value I'm looking for doesn't fall in between min and max, I don't touch that block. And then if I have multiple parameters, like I'm doing location and date and ID, we do an intersection of the blocks or the row numbers that need to be scanned and only scan the blocks that you need for. Now, that makes more sense if the data is in a particular order, right? So on Redshift, for example, imagine you have a completely unsorted table, and you make a query that you want to look for a particular date. Because of zone maps, even if the table is not sorted or the column is not your sort key, we will do the zone maps and try to skip the blocks as much as possible. But you see, it's a hit and miss. It's not that great. But if the table is sorted by that date, then I can only scan a single block. Now, the other difference between Redshift and a regular database that has indexes is that if you index in one column and you query a different column, you don't use the index. On Redshift, if you order by one column, but you query by a different column, however, the different column has a correlation with the first column. For example, order ID and date, they both grow to the right. Right? So if you sort by one, you're kind of sorting by the other as well, so you take advantage. May not be full advantage, 100% advantage, but maybe 80% advantage, and saves you a lot of time to scan your data. So on Redshift, you can create complex sort keys. You can choose one column or multiple columns. On the compound sort keys, the way it works is we sort by one column for the first column, and then for the same values of the first column, we sort by the other columns. Which means that you don't want a very high resolution column, the first column, because everything comes after that will be useless because you have a very high resolution. So contrary to think of on indexes where you put the most selective column first, on Redshift is actually the opposite. You put the least selective column that you query by first, because then you can take advantage of the multiple layers of your sort keys. In my example, if I'm searching by customer ID only, I can touch only the red block there. Simple, easy, efficient. But if I skip the customer ID and only query by product ID, and my sort key is customer ID, product ID, I will have to scan the whole table, which is not that bad on Redshift because you only scan that column and it's massive parallel, etc. But it's not ideal because it's a linear cost, right? The bigger my table is, the longer it takes, right? So a lot of customers say, you know, I have some tables that sometimes I query by one column, sometimes I query by other column. Can you help me have two sort keys that I can both query by one or the other? I don't have to always have the first column on. And the tendency is for us, you know, let's create a projection or a merge index, whatever, or join index, some different databases, right? We didn't want to have redundant data on the database because it will slow down the loads. So we got nerdy and came up with something called interleaved sort keys, where the 2 or up to 8 columns, they are sorted in an interleaved way. I sort a little bit by one column and a little bit by the other column. The way that works is like this. First, for each column that I'm having my interleaved index on, I map in buckets 1024 values, and I distribute the value in buckets, like a hash information. But I maintain the order. So I have buckets, I maintain the order. And then every value is given a bucket. Then I mix together the bits of the bucket values for every column. So then I maintain the order. So I still have the order. Like if I do a range search, I still can walk through and know when I don't have that column anymore. Right? It allows me to do range scans, but allow me to scan by product ID or by customer ID independently. Right? So the data will be sorted at equal measure on both keys. Now, if after I created my table and did my interleaved sort key, I have a new value that didn't exist before, there is others bucket. And of course, after a while, if you have too many of those new values, all your data is on the others bucket and is not efficient anymore. right? So the interleaved sort key works for columns where the values are kind of stable. And if you add too many new values, eventually you have to do maintenance on the table and remap and rewrite the whole table to incorporate the new mappings. That's what we call vacuum reindex, right? It is painful, it is slow, it sucks. We're gonna fix it one day, but not there today, okay? Now, in my example, right, let's say if I'm looking for one customer ID, instead of scanning 4 blocks on my example, I scan only 2 blocks. If I scan by a product ID, I also only scan 2 blocks instead of 4 blocks. So I get logarithmic access to the table. And it's much faster than nonlinear scalar, right? Now, interleaved sort key, as I explained to you, has some limitations. The first limitation only really makes sense on very, very large tables. Redshift is a massive parallel system, columnar, fully compressed blocks. So imagine a table where on a particular slice, on a particular CPU, I have 10 blocks of data on that column. That represents pretty much about 80 million rows, right? And only when I have about 10 blocks to scan is where the cost to scan the whole table is double the cost of scanning via interleaved sort key, right? Now, there is cost to load and maintain the interleaved sort key table. So it only really makes sense if your table is really, really big, right? Otherwise, it's not much difference. You see only after the 10 that the numbers kind of really go apart between the linear and the logarithmic one. And only makes sense if columns domain are stable, because if I put a date or timestamp on my table, the moment I build the table, the very next value that I insert goes to the others bucket. It's useless, right? I have to reindex all the time, right? And even that, we are thinking of finding a way to fix that. So the interleaved sort key can be a wider range of uses. Today, it's a quite narrow usage, but for that usage, it saves really, really a lot of time. But if you use for the wrong usage, especially if you use timestamp, it can cause you a headache. So keep an eye on that. Now, on Redshift, on the topic of trying to allow I/O to not happen, right? We compress everything and try to stay on the same place. We want to distribute the data as even as possible. So a choice of distribution key becomes very important. Is you have to make sure that you know where the data is going. And the idea is to be even distributed. If you have a skew and one node has way more data than others, everybody has to wait that one node. So you lose your parallelism, right? And you want to reduce the data movement, because you want to, when you join 2 tables, you want the rows of those 2 that are joining already together on the same node, so you don't have to move data around. So that's where you choose your distribution key. And on Redshift, you have 3 choices. Either you choose a column where we apply a hash function and put on the different slices, on the different nodes on the Redshift. And for 2 tables that have key distribution keys, to be able to actually fall on the same column when you join, the 2 columns actually have to be the same data type. I have customers that have one table with a key that is char and another key that is varchar, both distribution key, and they join together and don't understand why it's slow. Because the data types are different. A hash function will act differently on different data types. So data types have to be the same. The size and the type have to be the same. Or if you don't have such a column, you can't choose a column, or you don't have a good choice, you can ask the system to just distribute evenly the data around, right? We came up with a 3rd way. Imagine on a star schema where you have a few large tables that you can't choose the distribution key, but you have a bunch of smaller tables that you join that are not so small that you don't care, but you can't have a single distribution key for all of them because they're different tables, different dimensions. You can make the system to have a copy of the table on every node, not on every slice, on every node, and every slice on that node uses the data locally. And then you replicate the data a little bit, but for those joins, a star schema, it's much, much faster for you to use. Now, you talk to me, okay, how are we going to know all this? It's hard to understand, and I'm migrating from another system. I don't know about Redshift, how we do, and the documentation is complicated. Maybe it's not complicated, but it's long, it's big. I understand, it's big. It's a very long document. We keep changing, try to make it better, but it is complicated. So we have help for you. We can help you migrate your database for you. And that's a tool that's been out for a while, and we're adding features to this tool. It's called Schema Conversion Tool. The Schema Conversion Tool can point to your existing database, Oracle, Teradata, Netezza, Greenplum, read your schema, read the statistics of how you use your tables, how you query your tables, and build for you the schema for Redshift already optimized with the best sort key and the best distribution key. All you have to do is to implement, right? No, it's not perfect, but it's a very, very good first step. It's awesome. Now, the tool also can look at the code you have on your application, your Java code or scripts that are created for one of your source databases, what we call legacy databases, and it can convert those scripts into Redshift schema. So it converts your code, that SQL code, and converts your schema. Now, the latest feature we added to the schema conversion tool is one of the sources now is Redshift. You can have an existing Redshift cluster that you're not sure if it's optimal or not, point the tool to it, and it can create a new schema that is optimized for the way you use your data. So it can save you a lot of time and help you understand the choice of distribution key and sort key, because the tool gives you options. 80% certainty, this will be a good distribution key, 20% this will be a good, and so forth. Now, if you don't have time to build a custom dashboard for building queries like the King guys did, you can use Quickside. Because Quickside and Redshift are things that go well hand in hand together, because we kind of sit next to each other in development, and they build the Spice engine to read data already on Redshift columnar into the Spice engine that is columnar and allow you to navigate your data really, really fast and really, really easy. So I highly recommend, if you haven't looked into Quickside, it just became GA and has a whole life ahead of it, adding new features and cool stuff. I highly recommend you take a look to it. Now, one more thing about the batch sizes that Phil talked about is on Redshift, the parallelism for loads is defined by the number of files you load. So if you load one big file, only one CPU will be busy. So you're just using 6% of your performance. If you distribute your file into multiple files, at least one per slice, assuming the files are similar sizes, then you have the full performance of your copy command, right? So, review a little bit. How do you optimize your database for your queries? First, you periodically check the status of your table, see if you need stats or need vacuum, right? And you really have to take a look on something that's missing stats or table skew or columns that are not compressed or data that's not sorted. All that will, over time, kind of degrade your performance. It's like hygiene, right? You don't brush your teeth every day. And one day you have a big cavity and wonder, what happened yesterday that I have a cavity today? Well, it's not because of today. It's over time, you neglected your data. On Redshift, the more often you keep track of your data, you don't lose performance, and the maintenance itself is cheaper and faster. If you let it go too long, then the maintenance itself takes longer, right? So keep your data in hygiene in up to date, okay? And check the status of your cluster. Check your WLM queuing, commit queuing, database logs. Take a look on that, see what's going on, right? Don't assume them just like, yeah, every so often you have your toaster, you have to clean up the things underneath, right? Otherwise, there's a fire one day, right? So be careful with that, right? The optimizer specifically likes to have statistics about the tables. Now, because you have very wide tables, you say, I don't have time to gather stats on all my tables all the time. You can gather stats only on sort keys, distribution keys, and queries that you use on filter. That's enough for the optimizer to make good choices on the queries, right? You don't need to scan. Like, if you have the time, great. But if you don't, at least gather stats on sort keys, distribution keys, and filters, because that will make a difference between a good plan and a bad plan. And of course, table skew and unsorted table can become a problem over time, especially table skew, right? Just look at the skew, and if that skew index on the SVV table info is bigger than 5, you're in trouble, right? Please, please, please pay attention to that, okay? Now, one thing he talked about is to avoid modification of data at the same time, right? That's called the commit queue. On Redshift, the commit queue is single-threaded, cluster-wide. You can do multiple changes at the same time, but at commit time, they come together and they line up. So, and the locks on Redshift happen on a table level as well. So two people cannot change the same table at the same time. They can query and change at the same time. It's fully ACID, but you don't want to do it. So that's why for a single table, you want to keep single-threaded, and that will increase your throughput instead of decrease your throughput. Trying to do too many things on writes at the same time will decrease your throughput, and that's what we don't want to. Workload management queue, it's something on Redshift that's kind of misunderstood, and here's how I explain. On other systems, a single query cannot take over the whole cluster. So for you to take advantage of the $1 million you paid for your system, you have to run a bunch of queries at the same time. That's your idea. On Redshift, a single query can take and is designed to take the whole cluster. So you're not gaining anything by running 400 queries at the same time. The system was designed to run few queries very fast. And you can use workload management to line up your resources because your customers will try to come to the base at their pace, and you can regulate that to a certain degree. But you can look at Redshift and say, if I tune my WLM queue from 5 to 10, how much faster my whole workload ends? And from 10 to 20, how much faster? Until it doesn't get any faster, then you don't need to turn it on again. You keep it there and let the system handle, because at some point you're going to hit inverse scaling, where the churn of too many things running at the same time will actually make your run slower than faster. We keep working on optimizing the workload management queue, and there's some awesome new features coming up, and I highly recommend. There's a session tomorrow, 2:30 p.m., that Vidya is going to come and tell all the new features that we came last month and the next 2 months. I highly recommend, because unless you want to stay another hour here to go over them, no? Okay. So we will come tomorrow and talk and see the session about new features. But workload management queue, think of how you can optimize the throughput of your system. Don't think about concurrency. Think about throughput. And that's what we want to think about. Now, we put together over the years a bunch of tools for you to optimize your usage of Redshift. So there's a GitHub. It's open source. And open source means that you can contribute as well. You can say, hey, how about a script that does that? How about a script, or there's a problem here. We take suggestions all the time. I maintain the repository. And we have utilities, we have monitors, we have UDFs, we have scripts, views, we have column encoding utility to re-encode your system, to recompress your system if you want. We even have a tool, more recent, similar to what they did. They can look at your tables and see which tables need more vacuum and stats and run the scripts for you. So take a look on those GitHubs, and it's very, very, very useful for you to manage your system. Now, are we done? Are we kind of, Redshift is good enough, right? We don't really need to change anything, right? We're never done, right? So what's coming next? We're adding a ton of features on Redshift, and all the features we add on Redshift are always related to make it fast, to make it cheaper, to make it easier to use, right? And there will be a session tomorrow, BDM402. It's called What's New with Amazon Redshift. I highly recommend. Vidya is going to go over all the new features, a few things that we haven't announced yet. We normally don't do that, but there are a few things that are just about to be launched, so we want to talk to you about, right? Related to workload management queues, related to how we're going to get more queries throughput going to the system, talking about how you'll be able to have different ways of connecting to the database without having username and password directly, some kind of cool stuff coming up. So I highly recommend you take a look on that, right? And there's a few other sessions that are other customers that use Redshift to do their work, right? And they learn their lessons. And I really beg you to look back on the documentation on best practices. And now, with this understanding from today, read it again and understand the whys of we say do this and don't do that. We keep making the documentation better. We take suggestions. We try to fix as much as we can. And we really, really want our system to be like a toaster, that you just put your jobs in, make a few choices, and it runs, right? And you don't have to worry about too much. And we strive to make it better and better over time. I'm a recovering DBA that I love to have knobs on things, and I have my hands slapped all the time. No, we're not going to put a knob. If the system is going to choose the right value or going to automatically do the right thing, we don't add knobs, right? And that's how it has been since the beginning. But there are a few knobs that you can't escape. For example, on the toaster, the bagel button, right? What does the bagel button do, right? So the bagel button is it only turns on the heater on the inside, so the outside where the crust is, it doesn't burn. If you don't know that, you don't press the bagel button, you burn your cheese on your bagel, or you put the wrong way, right? For whatever reason, you're going to change the bagel, I don't know, right? But you have to know that, and not all toasters are the same. Some toasters, the outside don't turn on at all. My toaster, it turns out a little bit less, right? So you have to understand how things work so you can take full advantage of them. You don't need to be an expert on toaster, But you need to know to clean up the drawer underneath a little bit, and know what the buttons do and how to put your stuff in. And once you do this minimal and understand how things work, you can take full advantage of the system, right? And that's the idea for Redshift. We want to make a system that's going to keep evolving over time. We're not going to build a behemoth database like other databases. We're always going to be fast, cheap, and easy to use. And that's what I have for you today. Thank you.